Hello, you're welcome back. All right. So we are going to continue from where we stop, and we are still on electrolysis. Okay, we've actually treated the Faraday's laws. Okay, the first law and the second law, and of course, the only way the law will make sense, or what we've actually treated so far will make sense. All right, or we actually will be clear and will be understandable is when we look at problems and the solutions. Okay, so we are going to be solving some question in this video, and the question we are going to be looking at, they are typical examination question, right? In fact, the exam that you're going to be writing, these are the questions that you are going to encounter under electrolysis. Okay, so you should actually take note of them. Okay, so with these particular questions or these problems, I'll be able to illustrate how to use the formula that I gave you in the previous video. Okay, so I hope you can still remember those formula. I gave you one formula for Faraday first law and another formula for Faraday second law. All right, now let's start with the very first question that we have here on the screen. Okay, so solution. Now the question goes this way: calculate the quantity of electricity in coulombs required to liberate 10 grams of copper from copper compound, right? So the compound is actually copper compound. That is the electrolyte, okay? So you know very well, you know what we have to do, okay? First, we have to know the number of Faraday, because the number of Faraday will tell us the number of electricity, okay, based on the mole of the reaction or the redox reaction, right? Based on the, let me say, based on the number of electron that was transferred in the redox reaction. So how do we get to know that? Since we are talking about copper compound, right? You know very well that the copper compound, right, uh, um, can be CuSO4, but let me not assume it is CuSO4. But we know very well that if the electrolysis is actually electrolysis of copper, all right, what actually uh, the reaction that actually take place at the cathode is going to be the reduction of this copper 2 plus, right? So the number of electron that is transferred to the copper 2 plus so that it will be reduced is 2 electron, right? So this is the number of electron. So for copper 2 plus to be reduced, 2 electron is being transferred. Okay, so this 2 electron, copper 2 plus receive this 2 electron, then it is being reduced, okay, to simple copper metal that doesn't have any charge. All right. Okay, so now that will now lead us to the number of Faraday. So with this now we can get to know the number of Faraday. So the number of Faraday, of course, there are 2 electrons, okay? So that's going to be, you know, the formula NFE, okay? Number of electron multiplied by 1 Faraday. So, of course, NFE, number of electron multiplied by 1 Faraday. Number of electron is 2. Then multiply by 1 Faraday, which we use F, okay? So let's just use F to represent 1 Faraday. So the number of Faraday is 2F. So please take note of that. All right. So having gotten the number of Faraday, so what we're going to do now is to actually compare this number of Faraday is what is actually used to deposit 1 mole, right? 1 mole of this copper, 1 mole. So we're gonna do some comparison. Okay, so I've gotten the number of Faraday. Remember, there are 2 things you need to find out. All right, number of Faraday and of course the quantity of electricity. But in this case, the quantity of electricity, okay, the quantity of electricity is the unknown now, question mark. So let's compare. All right, I told you that to solve this you use proportion. So how do we solve it? So we can simply say that okay, so we can go this way. 2 Faraday actually deposited, okay, 2, 2 Faraday was used to liberate from this particular equation, okay, how many moles of copper was liberated. 2 Faraday was used to liberate 1 mole of copper. All right, So now I want to know the quantity of electricity Q. So Q, which of course is unknown, is actually used to liberate. Then we'll now go to what was given, okay? Because we are asked to find the quantity of electricity that is used to liberate 10 grams, okay? So the copper is 10 grams. So I have to convert that grams to mole since I'm comparing with mole, right? You know how we convert mass to amount in mole. To convert mass to mole, all we just need to do is to divide the mass by the molar mass. Okay, from the question, we'll know that the molar mass of copper, right, has already been given. That's 64. So it's going to be equal to, all right, 10 all over 64 mole, right, of copper. So now this is the proportion. Remember how we do proportion, okay? So for us to be able to solve using this proportion, all we just need to do is to cross multiply. So I'm telling you the shorter way of doing it in examination so that you get your answer very fast, okay? So all I just need to cross multiply. Q multiplied by 1, that is going to give me Q. All right, it's equal to, then what I'm having is 10 all over 64, then multiply by 2F. Okay, so of course that's going to be equal to 10 all over 64, right? Multiply by 2F. Of course, you know what F is, right? Faraday, Faraday constant, which of course is 96500 coulomb per mole. So we put that down here. Okay, 96500 coulomb per mole. All right, so at this point, you can possibly, all right, you need to use a calculator to help you calculate that amount there, right? Let's see what we can do. All right, so what we have is going to be 10 multiply by 2, then multiply by 96500, okay, then of course divided by 64. Okay, so 30156.25. 30156.25. And of course the SI unit is cool. So as simple as that. All right, let's look at another question. This is another question, okay? Now this one goes this way. The mass of silver deposited when current of 10 ampere is passed through a solution of silver. All right. Um, when it is actually passed through a solution of silver salt. Okay. So now, in this case, you know very well that as usual, all right, we are going to look at, we need to still find the number of Faradays. Then we'll now compare it to the quantity of electricity that was actually supplied. Okay, that's supplied. But first of all, let's get the number of Faraday. So solution. Okay, so how do we get the number of Faraday? Let's look at what happened with silver. Of course, you know that silver is Ag plus, right? So for silver to be discharged, it just needs one electron. Silver just needs one electron. Okay, so since silver needs one electron, that we actually, okay, cause it to be deposited as a just silver metal. All right, so that means the number of Faraday that is actually used for this particular reaction, redox reaction, is going to be equal to, of course, the number of electron is one electron, okay, multiplied by 1 Faraday, okay, so that's just 1 Faraday. All right, okay, so of course, you know what the next step is. Please pardon me. You know exactly what the next step is. The next step is we are going to evaluate the quantity of electricity. So this time around, the quantity of electricity that was supplied wasn't actually given. All right, no, it wasn't given. So the quantity of electricity, um, uh, the quantity of electricity wasn't given directly. We have to calculate it. Why? Because the current and the time was given. Remember, quantity of electricity is always given as current multiplied by time. Okay, don't forget that. Current was given. That's going to be 10, and of course the time is given. The time is 4 4.830 seconds. All right, so let's do that. If we multiply this, of course, we end up having 48300, okay, columns. All right, so we've gotten all we need now. We now, after getting the two, all right, the two quantities of electricity, one from the number of Faraday, the other from the quantity that was supplied, actually supplied to the solution, then we can now go by comparing. Okay, so right, so let's begin our proportion. So what is our proportion? First of all, we say that 1 Faraday, okay, is what is used to liberate 1 mole. Okay, so it's used to deposit, all right, 1 mole. Okay, 1 mole of silver. So now we now compare with this 48300 column that was supplied. Okay, so it's actually used to deposit the amount that we're looking for. Remember what we are being asked. Okay, we are asked to find the mass of silver that was deposited. Are we good now? Yes, I hope so. So we are looking for the mass of silver. Now remember, I'm comparing with mole. So that mass I'm looking for, I have to convert it to mole. Remember, converting mass to mole, you have to divide by molar mass. Okay, so now the question is, what is the molar mass of silver? Was it given? All right, the molar mass of silver is 108, if I'm not mistaken. Okay, okay, if I'm not mistaken. But if I'm mistaken, of course, it's supposed to in the exam it should always be given. Okay. Oh, uh, should I confirm? Okay, let me just use that 108. All right. Okay, so it is in exams. Don't bother about the molar mass. Just like what the very first question. Okay, under the question, okay, the molar mass of that particular ion will always be given. Okay, so as we now m all over 108. Okay, of silver. All right. So you know what we do? We cross multiply. So I'm going to have m all over 108, then multiply by 1 Faraday. 1 Faraday, of course, is 96500. Is equal to 4 48300. Of course, multiply by 1. Okay. So, of course, you know very well that for me to be able to find m, I have to cross multiply. Then, of course, divide by this. Cross multiply, I'm having 48300, right? Times 100. Then, of course, divided by 96500. Okay, let's do that. Okay, 48300 times 100. Okay, right? Then divided by 96500. Okay, so 50.1 approximately. So 50.1 grams. Okay, so you see, I believe it's now making sense now. The procedures, the step, right? I believe it's making sense by now. All right, so let's look at another question. Now, this one right here, okay? Let me bring it. This question right here is the question that is, of course, that is actually based on a Faraday's second law. Okay, so we are going to use Faraday's second law to solve this. Now, the question goes this way. Okay, if a given quantity of electricity liberates 0.65 grams of zinc Z2 plus, what amount of Hg2 plus will be liberated by the same quantity of electricity? Remember, we apply Faraday's second law when the same quantity of electricity is passed, okay, into two different electrolytes having, all right, two different ions. Okay, so I hope you can still remember the formula for Faraday. The formula I gave you for Faraday's second law. Please don't forget it. Okay, remember what I gave you. The amount of the ion 1 multiplied by the charge of ion 1 is equal to the amount of ion 2, then multiply by the charge of ion 2. Okay. Now, of course, you know that the amount in mole, the amount here is in mole, right? So we have to convert the mass to mole. So the ion 1 here is zinc, okay? So the amount of zinc is going to be the mass of zinc, remember, divided by the molar mass of zinc. So that's going to be 0.65. Then, of course, divided by the molar mass of zinc, which is 65. Then multiply by the charge of the zinc. Zinc is 2 plus, so the charge is 2. Okay, it's equal to the amount of mercury, all right, um, is what you are looking for. We are looking for the mass of mercury, right? So what amount of mercury? Okay, basically that's going to be the mass, the amount of mass. Then of course divided by the molar mass of mercury. That's 201. Okay. Then multiply by the charge of mercury, which of course is 2. So they're having the same charge. Of course, it is easier for me to just cancel out the 2. Okay. So to now solve for my m, all I just need to do is to cross multiply. So the mass is going to be equal to 0.65, then multiply by 201, all right? Then of course divided by 65. Okay, so here we go. So 0.65 multiplied by 201, okay? Then divided by 65. All right, as simple as that. So the mass is 2.01 gram. So I'm very sure with these few questions, okay, have given you right the understanding on how to apply Faraday first and second law, right? So we are going to look at more examples, right? And if there are more questions, we're going to look at them in the next video, all right? So see you in the next video. Thank you very much.